Welcome to our virtual poster. I'm Johan and I'll be presenting our robust dense match RoMa. This work is a collaboration with Chiu Sun, Georg Böckman, Morten Wadenbeck and Mikael Persberg. Let's get into what our method does. RoMa estimates dense correspondences between almost any two images of a 3D scene. This means that we are able to create accurate, dense 3D reconstructions, even for very difficult in-the-wild image pairs, such as the pair you see on the poster. Dense matching involves estimating a matching coordinate in every pixel, called a warp, as well as a confidence for the match. We follow the standard approach, which is to estimate a coarse warp from coarse features, followed by refining the warp with fine features. Starting from the top left, coarse features are extracted for both images, and matches are somehow encoded, for example as a correlation volume. These are decoded into an initial coarse warp, which is then refined using fine features. All this is trained using matching losses, where we compare the predicted warp and confidence to some ground truth warp and confidence. Typically, this ground truth comes from multi-view stereo. Let's go into further details on the method. We start from the recent state-of-the-art dense matching model DKM. Our first insight is that we can gain performance from separating the fine and coarse feature extractor. As can be seen in the table on the right, if we use two different networks for fine and coarse features, we generally get better performance. We additionally find that if we use a specialized network for the fine features, such as a VGD19 instead of a ResNet50, we can further improve performance. These results indicate that coarse discriminability and fine localizability are in some sense in tension, and there is a trade-off when training these jointly. Separating it into two different networks helps with this issue. We next investigate changing the architecture of the match decoder. Here we find that removing as much locality bias as possible helps. To this end, we change the architecture from a convnet to a transformer and do not employ position encodings. We next further improve the coarse robustness by replacing the coarse feature encoder with a frozen Dyno V2. This enables our matcher to generalize significantly better. We also improve the loss terms. In particular, we change the coarse loss into a regression by classification loss and use a robust regression loss for the refinement. As a final note, we found that our proposed transformer match decoder was particularly useful in our final setup, as can be seen by the performance drop when replacing it at the bottom of the table. We think this is due to less locality bias being needed. Let's have a brief look at the results. We observe a general boost on all benchmarks. Most encouraging is perhaps that our improvements are largest on the most difficult benchmarks. We visualize some estimated warps, with white here indicating uncertainty. As can be seen, RoMa is able to estimate reliable correspondence even in extremely difficult cases. Code for RoMa is available on GitHub. Thanks for listening, and I hope to meet you at the poster session.